First of all, I have to say it's my pleasure to be here. Thank you very much, Alexander, for your invitation and for this possibility to visit our Russian team with this very good conference. So I think all in all, it's better to speak and to discuss, not to do another things which are going on now. And I will say about scientific work which going on in our institute, even in our research center. I want to start from 4 logos located in this point. I want to start from these 4 logos. First one, it's logo of Russian Academy of Sciences. Our institute belongs to Russian Academy of Sciences, and this year it's universal year for us. We are celebrating 300 years. Russian Academy of Sciences is one of the oldest academy in the world, and it still operates. And now there are about 400 research institutes belong to Russian Academy of Sciences. Russian Academy of Sciences has 4 branches, and we belong to Ural branches of Russian Academy of Sciences. It's a regional branch, about 30 research institute and 8 federal research centers. And I'm head of one of the research center located in Perm, and you can see the logo of our research center. And finally, I will speak about one small laboratory inside this center. I'm not head of this laboratory, but I still keep research position in this laboratory. And we are working with very interesting technique called leather shock pinning. And this technique, from my point of view, one promising technique to increase the fatigue life of many metal structures. Filippo, a few minutes ago, said that failure and fracture is a local process. And leather shock pinning give you unique opportunity for local, to get a local effect on your fatigue materials. It's very effective even with stress concentrator. So next slide presents our our geographical position. You can imagine the size of Russian Federation. We are located in we are say in the middle, but it's geographical middle of Russia. It's border between Europe and Asia, geographical border. We are located in European part of Russia. And our research center has 6 research institutes. It's more than 1,000 people inside of the center. And one of these institutes working in this area of structural integrity, Institute of Continuum Media Mechanics. And due to that we have 6 institutes, we are easily to start interdisciplinary research. It's very interesting. We have a lot of research in mining industry, in mechanical chemical industry, and mechanical biology industry. But Institute of Continuum Media Mechanics and one of the laboratory of this institute. So this slide presents outline of this presentation. In the beginning, I will say several words about technique. Maybe you're not familiar with this technique, maybe you know it, but many times when you send your paper to the international journal, where people ask you about temperature, about laser welding, about some process with laser. But laser shock pinning, it's quite different process. And next slide will present the physical background for this process. After, I will say several words about development on scientific basis for application of this technique, and it's really important. In Russia, we say, if you want to do something, to create something setup, industrial setup, you have to know in 10 times more in fundamental size. In this case, your setup will be successful. So our institute belongs to Academy of Sciences. We are working in fundamental research, and we start very wide fundamental research to find all scientific basis for this technique. And from my point of view, it's quite interesting. And after I will show the Russian setup assembled in my institute. And from my point of view, we have at least 2 advantages. We can measure stress strain impact in real time, and we can measure the distribution of residual stress. So we can investigate all peculiarities of these processes and find the optimal region for treatment. And finally, I'm not going into detail about structural investigation. It's quite interesting. We can discuss. It's still there are a lot of still open questions, but I will show just results for samples with stress concentrator. And for me, it's quite amazing. We can increase fatigue life in 10 times. If you find the optimal regime, it's not 10, 20%, it's times. Okay, and if we are going to the next slide, yeah, it's laser shock pinning. I will show the movie. It's not our movie, but you can have an idea about what's going on. The idea is quite simple. You have very strong laser, very strong and very short. The power density is quite high. It's about 90 gigawatts per centimeter square, and you are immediately evaporate the material. Due to evaporation, you generate weak shock wave, elastoplastic wave, very specific shock wave, with very high amplitude and with very short duration. Short duration is quite important. The physical mechanisms behind plastic deformation is quite unusual for me. And this stress wave propagate in the sample, and you are able to create compressive residual stress in the depth up to 1 to millimeter. And the value of this stress is up to -1 gigawatts. So it's incredible high residual stress, and practically you can keep all cracks, you can keep all initial defects, and finally, as a consequence, you can increase the fatigue life. So you can read the ideas of this technique, and you can see what's going on. We have a water layer and laser pulse, and after plastic deformation. So it's very funny story. About 3 years ago, I'm not going to work in laser shock pinning. I have very good friends in Germany. They developed this technique for Airbus, and they told me, you're working with fatigue cracks. There are very good technique to drive the fatigue crack propagation. Could you try? And he have shown laser shock pinning. It's result from colleagues from his colleagues from Germany. You can see the standard samples. Blue square, it's area of treatment, and red line, it's fatigue crack propagation in initial case. And if you apply different regions of laser shock pinning, you can see the slowdown of fatigue crack propagation. Yeah, it's quite expected, and you have technique to manage, to drive the fatigue crack propagation. And practically, if you have crack, you can stop it, or you can prevent crack initiation. Next slide was absolutely magic for me. When German colleagues showed me, it was absolutely fantastic. It's well joined, and cracks with well joined, and you can see the standard Wheeler curve. It's standard Wheeler curve for these samples. If you have crack, of course, the fatigue life decrease. It's expected. But if you take a samples with crack and treat it, the fatigue life increase, and it's possible situation when cracked sample stay better than initial sample. It's absolutely fantastic. So after I say, okay, we should develop this technique. There are at least 2 themes which works in the United States, even in Germany, and we cannot find this setup, this equipment in Russian Federation. It was about 3 years ago. It was absolutely free. We start to work, and we develop. We're not going to buy this setup. We developed this setup in Russia using help of our Chinese colleagues. We are both the laser robots and so on. And together with German colleagues, I think the next slide will present, with collaboration agreement, which was signed, I guess, in 220. But in 222, it was completely forbidden for German colleagues, even personal contacts with Russians. But in this case, we finished this setup and we start with work, and it's really pity, but we are waiting for start again this collaboration. So the preliminary result, we sent our colleagues, Lena, to Germany, and it's quite simple experiments with titanium or T4. It's Russian titanium. I don't know exactly the equivalent alloy in abroad, but you can see residual stress, 1 millimeter from each side, up to 500 megapascal, and it's good even both. It's good both for low cyclic fatigue and for high cyclic fatigue. And we decided to start this work in Russia. Now we have experimental setup. We can treat practically any shape of the samples, any materials. The power density in this setup is bigger than setup of United States. And if you are reading about this technique, it's really magic wand. You can increase hardness, corrosion resistance, resistance to fatigue life, wear resistance, durability. You can healing fatigue crack. You can do all what you want. It's absolutely fantastic, but it's not true, of course. Yeah, it's good to be true, exactly. But if you compare short pinning, the standard technique which was used in our industry, and laser short pinning, you can see easily it's bigger and deeper. But there is at least one problem. If you have such technique, all in all, you have a balance. If you create residual stress, compressive residual stress in one place, you create positive residual stress in another place. It could be inside of a sample, it could be on the sample surface. And it's really a big problem. And I have only a few minutes. I just show you what we are doing. We find 4 steps to apply this technology to the industry. First step, we have to investigate the physics. We have to investigate the physics of plasma and calculate the stress spread, strain time, the dependence of the impulse. Second one, we have to calculate plastic information, very specific plastic. And up to now, we use quite simple approach, which include in standard software. After, we have to calculate the residual stress. We have to simulate the process with complex shape. And finally, we have to investigate the effect of effect. We have solved all steps, not fully solved, but we have solution for each step, and we can move from the beginning to the end and to focus on the result. Our advantage, we have 2 additional experimental setup in our lab. We have Weiser or photonic Doppler interferometry to measure the real pulse, and we can measure the residual stress. So I'm not going into detail, I just go into the final slide, and you can see the result. It's 3 kinds of samples, 3 different titanium alloys. For example, in this, you can increase the particular intensity to time. But what I want to show, if you find the good position of treatment, for example, this sample with stress concentrator, we have tested 5 different regions of treatment. We can increase fatigue life in 7-8 times. So if you are able to simulate this process, and now we are able to simulate, if you're able to forecast the distribution of residual stress, you can find the optimal position, and you can easily to treat real metallic samples, and results quite promising. So, sorry, I have no time to go into detail. If you're interested, we're open for collaboration, and we have still a lot of open process. Its conclusions, it's just a look of Russia. Now it's near our place. It's not Photoshop, it's real picture. So feel the spirit of Russian Federation. and welcome to us. Thank you very much for it.